Hey, Kevin, can you hear me? Kevin, can you hear me? Hi, Kevin, can you hear me? Hi, Kevin, are you there? Can you hear me? Hey, Kevin, can you hear me?
Yeah, I can.
Oh, good. Okay. Hey, just so you know, we might be joined by Tabichi. And
Tabichi?
yeah, Tabichi's a little bit late to join. He's apparently very smart, but he does have some challenges. And we'll see. Hopefully he joins us. And just be patient with him, and hopefully he takes off with this. He does definitely have some very strong math skills, so it'll be interesting to see how this goes. He may not join. We'll see.
Just pardon. Who is Tabichi though?
Tabichi is a grade 10 student, and
grade 10? Okay.
grade 10, yeah. So
I started recording, so
okay.
So let's cover Q. Wait, I think we covered Q, right? No, we haven't. Okay. So in short, Q is a type of data structure, and if we find an image of Q, this is basically a Q. So for Q, a new person enters from the back and leaves at the front. So let's simulate this actually. So if there are like 3 people here in a queue. With my drawing. Okay. So the queue is facing this way. If we want to force people to join, this person will be joining from the end of the queue. And in case they're waiting for something, then the first person will leave for the first. So he will leave. And if there's another person, he will join from the back. So like this. And for the person to leave, the first person will be the first to leave now. So he leaves. Okay, that's it. So that's what a queue is like in real life. And in competitive programming or in CompSci, we have a data structure called queue to simulate this process. So there are 3 main processes. Firstly, we need to, for queue, it supports several operations. So the first one will be enqueue, which means enter the queue. Second one will be pop. Let's say dequeue. Or let's just say leaving the queue. And that's it. So for enqueue, we will enter from the back. For leaving the queue, we leave from the front. So for the queue, the first person who enters will be the first who leaves. So we call it FIFO, which stands for first in, first out. This is an important thing for queue. Okay. So after knowing the logic structure of the queue, we will try to simulate it, or we can just create a queue now. So, question now, Carol?
No.
No? Okay. So, okay. So, let's simulate. Okay. In the header, we'll have to include queue, or we just include it's so this library that we are including, it's the standard header library, which contains every library in the standard library. So everything in the C++ standard is included in this library. So if you find like including several lines are too long to write, you can just write this instead of including 5 libraries or more. Include queue required for us to use queue. So we want to create a queue now. As I said last meeting, we learn about stack, right? So for C++ container, they're called container. This is the name of the container. Sorry, this is the type of container, and inside is the type of elements that's being stored, which is integer here. And after that, this is the name. We'll just call it Q. I will use capital Q, upper Q. So we created okay. So Q supports, let's see. This is not operation. This is specialty. So the first operation we need is enter the queue. Oh, we need the third is visiting the front of the queue, which is the first person. So for the first operation, we want to enqueue, which is in this queue, we want a person to enter the queue from the back. So queue push, that's what we want to do. So if I want to add a number 10 in queue, I'll just write queue.push 10. And if we want to visit the front of the queue, which is the first person in the queue, we'll just output queue.front. Remember to write brackets here because it's a function. So and if we want to let the front person leave the queue, we can use queue.pop. And we don't need any parameters for this function because it just pops the first person in the queue, which doesn't matter who the person is. So now we can, this is the implementation. This is how we use queue as a data structure defined in C++ standard template library. So that's it. and we can simulate to see how it works. So now we have a, let's see. Now we have a queue. Queue. And we want to push number 10. So currently the queue has a number 10. And we push queue has 10 and 20. And if we pop, which let the first number leaves the queue, so the queue now has only 20. Then we want to output queue.front to see our operation if it's fine. Okay, yeah, don't forget to write using namespace std if we want to use any functions or other structures defined in the standard library. So we want to use standard by default. Okay. So let's check our results. Here it outputs 20. And there are other things we can do with this. So as a data structure, it's important to know if the queue is empty or not. So queue actually supports showing the current, I'll say if it is empty or not. So it's, let's see, if queue.empty, because queue.empty function returns a Boolean value, so returns either true or false, telling us if the queue is empty now or not. So let's queue.empty, out empty. So when we first create a queue, by default, there's no element in the queue. So it should output empty here. And if we push in 2 elements, but we pop the first one out, currently there should be only 1 element left. So it's still not empty. So let's try. Okay. As we can see here, it only outputs empty here, which is from here, because it still has an element here, which shouldn't output empty. Okay. So that's what queue can do. So as I said last meeting, that structure, they don't do much work themselves, but they have to work with powerful algorithms that fits their specialty. Then they can work really, like they can have more powerful use. So breadth first search is highly related to queue, which we just use in short BFS. Okay, so we mentioned DFS last meeting, and DFS, which has a similar name. So I think DFS or depth first search. Okay. So depth first search, it's basically, if you choose a path, you just go to the end until there's no way to go. Otherwise, you will choose this path, stick to the end, then come back for another path. But BFS is the, I would say, opposite. You go, imagine you have 5 directions now, and you will take a step in each direction, and take another step in each direction. So let's draw a graph. So let's see, if you are on a road now, imagine there's a road. We are going this way. There are 3 ways to go now. There are 3 ways to go. This is 1, 2, 3. What DFS does is it goes, you choose 1, you go to the end of 1, it ends, then you come back, you go to the second row, you go to the end, you come back, you go to the third row, until the ends, you come back. What BFS does is, so it's BFS now. You take a step, you take another step here, you take another step here. Then from here, you take another step. But it's important that this algorithm requires a way to store its current state, because you take a step here, you have to kind of memorize you are here currently. So when you come back, you can move another step starting from here instead of starting from the original point. So as we can see, BFS requires a way to save our current state, where we were, where we are, after taking the step. So we store this state, we go to second row. We were here before, so we take another step from here. And we store the state, which we are here now. Then we come to the third row. We go to this point, since we were here last time. So we take another step, and we store it here. Okay, then we come back to the first row, go another step. So it's really different. These two are like opposite approaches. And as we can find out, there's a weird pattern here. So in the first round, let's say round one, you're at road 1 first, which is R1, R2, then R3, right? You take a step in each road, then round 2, we start from R1 again. And using Q, so imagine there's a Q. Now. So we push in R1, then R2, then R3. We push them from the back. Then in the second round, which I want to restart everything, I will take out the front one, which is the R1, and pop it. Then I start walking on road 1. After walking, I record my current state. So I push it from the Q's end, which is pushing from the back of Q. Then I choose to go on row 2, which I read my previous state, pop it. Okay, then I take a step and I record it, which is in Q from the back. Then I go to row 3, and I have to visit the front one. So use this again. Then I take a step and record my state, push it in the Q, R3. So you can see here, Q actually helps us to keep in track of our state in each direction. Or maybe after each step, I would say. Because we will change often. So this is the reason we want to use Q. It's a first in, first out data structure, as I said before. First in, first out. So the first pass you take is the first pass you will take again. So you can keep them in order. Otherwise, imagine we're using stack, So for stack, if the last one is the top, so we have R1, then R2, then R3. In the second round, we take out R3. And we push R3. So we take out R3, we record, put it back again. Then we take out the top, which is still R3. So stack cannot do this task. So that's the difference. And that's the reason why we choose queue instead of stack, because it can do the work that stack can't. Any question now? On
No.
like, no? Okay. So let's see. So BFS is kind of hard actually. So a reason why we don't use BFS. So some good points and bad points. I will just implement BFS first. Okay. So different thing is, so for DFS, which is stack for search, we use the function, right? Because we have to do recursion, we have to call the function recursively, so we have to make it a function. But for BFS, many times we don't really write it as a function. It doesn't matter because we don't use recursion in BFS. That's a different difference. So for using BFS, we can avoid recursion. This is a good thing because BFS is more reliable, but it also takes time to implement because DFS is easier to write, easier to implement, and easier to think, while BFS has a longer code. So let's use a graph though. I'll just take a simple question in BFS. Give me a sec. So we'll find the classic question. Okay, let's ignore that. So a classic kind of question for BFS is used. So sometimes we use BFS to find the shortest path. This is powerful because most shortest path questions require third algorithm. Without the algorithm, it's impossible to solve. And BFS can solve the question. Okay, I think I will cover some graph before talking more about BFS. So in COMSAT graph, it's not a graph that you are just drawing. Usually we are talking about some vertices. So in a graph, there are vertices, and there are lines that connect them, which is called edge. So it has vertex or vertices and edges. So if we have such a graph, then the graph will be, let's say it's vertex 1, 2, 1, 2, and 3. And from 1 to 3, there is an edge starting from 1 pointing to 3. So there can also be an edge from 2 to 1. There can also be an edge from 2 to 3. Okay. So that's the thing we're talking about. And in CompSci, there are certain ways to store a graph. So let's say, so a easier approach is using a 2D array. To give some hint, it's just using a 2D array. So there are 2 dimensions, right, in the 2D array. The first dimension can be starting point, which we use U, and the second dimension is the ending point, which is V. So we can use, so if we use 2D array to store it, which we just call it adjacent table, I think, adjacency table, if that's the correct name. Okay, so we have an array. It has 2 dimensions. The first dimension is U. The second dimension is V. It records the cost from U to V. We use cost here, or it depends. It can be the time cost from U to V, or the material cost to build a row from U to V, or the length from U to V. So we just use the cost for it. So ARR UV equals cost, which means the cost from U to V. Okay, so this is our first way to store it. But as I mentioned in last meeting, we talk about time complexity and memory complexity, right? So memory complexity are similar to time complexity. So if we have, let's see, we have 1,000 points, or 10 to the power of 3 points, right? And an array is 2-dimensional, so it takes us 10 to the power of 6, let's say, units to store the data. So this is not efficient. Let's see. So if we have 1,000 points and there are only like 20 edges, then we still have to use 10 to the power of 6 units to store the data, which is pretty naive approach for us. We shouldn't do that, right? Any question here about the memory?
No.
No? Okay. So when the edges are not too many, or let's say when the graph doesn't have too much edges that requires us to use adjacent table, adjacency table, yeah, I think it's, then we can use, oh, that's called the adjacency matrix. It's not table, adjacency list, yes. Okay, we can use adjacency list. So adjacency list, you can think of an array, but an array has multi-dimension. For each dimension, you have a vector, I will say. So there's an array storing, so let's see, it's hard to simulate here. So if we have an array 0, it stores, let's say 1. It stores every point connected, or let's say starting from U to V. So it stores, so ARU, it has a V equals cost, but it's different here. Here we use a, let's say we use a dynamic array, which we haven't covered, but we can think of. So you can think there's a array called ARU, and if you have a new point, oh, it shouldn't be like that. So ARU, now if you add a new point, which is called whatever V. So V is the destination of that we can reach from U. So let's say V1, it tells us we can go from U to V1. So which tells us there's an edge from U to V1. Then if there's another edge, we can add it here, V1, V2. So we only add points when they are required. So there's no extra spaces wasted here. Imagine if there's a point called AR3, then we can see there's no points where we can start from 3 and go to. So if U equals 3, there's no valid V for us. So AR3 is empty. We just don't put anything in, so we can save those memory for other points which needs memory. So adjacency list saves many memory for us. That's a good point. And it requires dynamic array. It requires linked list or dynamic array. We haven't learned. But dynamic array are just as same as normal array, so they are easy to understand. Let's talk about dynamic array here, actually. Any question on the stuff I just talked? I think I talked too quick. Any question, Kara? Okay, I think no question. Okay. So dynamic array. In C++, we use it. So it is implemented in vector library. So same as all containers in C++ standard library, we use vector. It is called vector. So this is the type of the container. We want to store, let's say, integer, and we call this vector v. We created a vector of v storing integer. So vector is the type, integer is the type of elements that we're storing, and the name is v. Okay. So v supports several operations. We just use the most common ones because there are many of them. So pushback, v.pushback, that's the same as the push for stack and queue. So you push element from the back of the vector. So currently v is empty. If we push 10, so v.pushback 10, v is currently 10. I mean, it's not 10, it stores only one element, and the value of element is 10. We can also push back 15, and v stores 10, then 15 now. Okay. Then we can also pop back. So it will pop the last element, so v will become 10 now. Vector also supports the operation as normal array. So for an array, let's say if we have an array 1, 2, stores 1, 2, and 3, we can visit the array using index. Let's say index 0. If we print out index 0, it will be 1. We can also do the same thing to the vector. So we can use cout v0, which is visiting the first element of the array, which is 10 and 9. Let's see what happened. Oh, didn't include in our string. Okay. So we can see the result here is 1 and 10. So we output 1 here, which is the first element, and 10 here, which is the first element in vector v. So let's say vector is, I would say, similar to array, but with extra features. So these are the basic, oh, there's still some. So we can read our sides. So this is a function that returns the sides of vector. So if it stores, let's say it stores one element only, then v.sides will return 1. So we can output the sides if we want. It also supports empty function. So which returns a bool, and this is same as stack and queue. So if v.empty, we can output something. We can make certain operation because it returns a Boolean value to use in if and else. I mean, yeah. Okay. So with vector, we can push element from the back. And if we don't have any elements that want to push, it won't waste the memory. So this is why we can implement adjacency list. We can, so if we get a pair, if we have a edge from U to V, we can do, say, let's call the vector G. So GU dot push back V. Then we store the edge from U to V. And if the edge is non-directional, which means it doesn't have a direction, it has two directions. You can go from U to V and go from V to U. Then all you need to do is do it twice. GV dot push back U. So by doing this, we store two edges from U to V and from V to U, which is the same as a bidirectional path. Okay, and this is the most important thing for graph theory, because when we interact more with graph, we will have to do some searching, some path finding, which means you have to find the shortest path, but not on matrix as we do last class, but on some real graph. They're like a map where you have one place and a certain distance from another place. Let's say if we get a map of British Columbia, right? Then I want to start from Coquitlam and go to Maple Ridge. There will be many stations with different distances. So you can use graph finding algorithm to find the shortest path. And GPS does the same thing. So I think GPS uses Dijkstra, let's say it's called Dijkstra algorithm, to find the shortest path for us to travel. So graph algorithms are really powerful, and they are one of the hardest topics. Yeah, I think I've just talked for 40 minutes without any pausing. So any question, Kara?
No.
No? Okay. I'll just assign you a programming challenge. You can spend some time on it. Okay. Okay. Give me a sec. Oh, okay. Okay. Let me find your question that isn't too hard. It's still solvable. Okay. So we don't want to do any graph problems now since they are too early for us. Okay. It seems too hard actually. Okay. So the question is for we'll start a contest which you can solve the problem. So May 19. It's from Katie's jump. Spell it right? Julie jump. Yes. So it's a question about array. I'll just start a contest now. You can solve them. Solve it, actually not solve them. Only one question. So you can kind of work on it. Okay. If you enter the group and check the contest, it will start after 1 minute. Okay.
Okay.
Are you in the group?
No, I need to go in there.
Oh, okay. Did you create an account yet?
No, I didn't.
Okay. You can just create an account and kind of solve it.
Okay.
So this is the website.
Okay.
Any comments, Mr. Kingsland?
No, I'm just sitting back here actually doing some work, some marking, but I'm listening with one ear and it sounds pretty intensive. Wow, keep up the good work.
Okay, thank you. I will upload the source code. And if you get stuck, we can kind of go through this problem. Or wait, I haven't invited you yet. Okay. So this is the link. If you have an account, you can just start solving it now. You don't have to join the group actually. So we'll go through this problem, I think. Jolly jumpers. Have you read the problem?
I'm reading it.
Okay. Okay. Any idea yet?
No.
No? Okay, then we can kind of go through some thinking process.
What is a
So-
successive element?
Oh, so successive, it's like consecutive or just adjacent.
Oh, okay.
So only the elements beside you. So for 3, the successive element is about 1 and 2. So it's either 1 and 4 or 4 and 2 and 2 and 3, kind of like that.
Think I get it a bit. Yeah.
Okay. So for the sequence, if the absolute value of the difference between 2 adjacent elements take on all the values 1 through n minus 1, then it's Jolie, otherwise it's not.
Oh, okay. Could you show how to do it? I just don't know how to start it.
So for this question, when I practiced CP for 5 months, I would say, no, 3 months, I got stuck for 3 hours. So
Oh.
I would say it's hard in a way, but it tells us an important stuff. So let's see, I will draw a graph still. So we can kind of find this is one of the most important tool in CP, which we are solving the problem for. So let's see. We start from the sample or from the example it's given. So for this sequence, 1, 4, 2, 3, 1, 4, 2, 3. So the difference between first two is 3. The difference between 2 and second is 2. Difference between third and fourth is 1. So it wants to take on all the values from 1 through n minus 1. So when n equals 4 here, the values have to be from 1 to 3. So 1 to n minus 1. So this is the pattern that we want to follow. Then we want to think of certain approaches. So it requires us the difference has to be one of, so all these numbers, they have to appear in the difference. So every number so no number can be missed. If there's any number missing from 1 to n minus 1, then it's not Jolie.
Oh.
Yes. Wait. I'm not sure. How does it mean? take on all the values. Oh, there are actually two constraints. So firstly, they have to take on the values through 1 to n minus 1, which means the condition, so the requirement 1. So the difference between A and A2 has to be between 1 and n minus 1. It also wants us to take on all the values, which means the language is kind of weird. I think they want all numbers from 1 to n minus 1 to appear as difference, right? So all these numbers should appear as the difference of successive elements difference. So let's see, these numbers are linear. They are adjacent also. So the array from 1 to n minus 1, it should fit our requirement. I mean, so if we create an array from n to minus 1, and when we find out any of them, we cross it out, marking on it. And if every number is marked, then it's Jolie. Otherwise, if we find anyone unmarked, it's not Jolie. Right.
Okay.
So, any idea on the implementation part?
Which part?
Implementation, which means if we want to write.
I'm not sure.
So, what structure do we use? We can use a single number, so we have to use an array, right? So we want to use an array. And if we want to make some mark, or just to mark if it's present or not, there are only two possibilities. It's either present or not present. So for this kind of stuff, we can use bool. We can use bool value because it has only true or false. It's just two states, either true or false. It's false. If it appears, it's true then. So Boolean favorite should fit our requirement. And this is, I would say, array of Boolean, or like bool array. It's the most important stuff in CP. Like, it doesn't seem too hard, right? It's the basic stuff, but whenever you want to record if that's anything in the range x to y must appear, then you will use an array of Boolean to keep off track of them, because you have to make sure every single one is present. If anyone is not present, then the result is false. The result is, I would say, no. Then you want to, so we want to use an array, then we linear scan each of them. So let's say we use a array of bool to false. Then whenever we calculate a new difference, we mark the number true. And at the end, if any number in this array of Boolean is not true, we will know that there's something wrong. We output not Jolie. Otherwise, we output Jolie. So that's the approach. knowing the approach is still different from writing the code. So some like wait, let me see. Remember, there's the code sharing stuff. Yeah. Do we have time now? Okay. I don't know if you want to leave or not. You can kind of read some code if you want, or not. I don't know.
Pardon?
You can write some code, or if you don't want, then just fine. A link which you can write your code, and we kind of, I don't know, go through the code and maybe make some changes so we can solve the problem.
Well,
Kevin, we should end pretty soon. I have to go. I got to go make dinner. So
Okay. Let's see. I'll just leave as exercise, I think. Okay. I will save this. So this is the approach question, and you can try to implement it.
okay.
Or if you find it too hard to implement, I will take my implementation. You can read it through if you get time, and that's it, I think.
Okay.
Yeah.
Okay, thank you. Bye.
Okay, see you.
have a good night.
You too.
Hey, so Kevin,
Yeah.
maybe what you could do, if you don't mind, is I'm not sure if to be next week, but if you want to, maybe come by my room tomorrow at some point, or on Tuesday, and
Okay.
I'll see if I can introduce you to him, just so you know, because as I say, he does. I think he's autistic, I believe, and so he does have some challenges, but he is apparently very smart. So. And he was his learning assistant told me that he was interested in coming out to the club. So maybe if you met him, then we'll see if he's interested left. But at least if he does want to have a look at the club, that'd be the best thing would be to come to a meeting.
Okay. Yeah. I will go to your room tomorrow, I think.
Okay, sounds good. Maybe during lunch or something, and then we can head down there.
Okay. Yeah, 11:20,
Okay.
I think.
Yeah, 11:20 is perfect. Yeah. All right. Thanks, Kevin. Good work today. My gosh, you sure know your stuff. It's very, very impressive. Keep up the good work.
Okay.
All
See
right.
you.